Hi folks, welcome to the third part of Defect Chemistry of Ceramics. Up to last lecture, we learned almost all the basic principles of defect chemistry, okay, up to this point. And now today, we are going to learn the defect structure of pure stoichiometric compound and impure stoichiometric compound. Here I mean the defect structure. Each possible defect concentration as a function of thermodynamic variables. And as regarding the thermodynamic variables, you may take all intensive independent variables or mixed variables, namely intensive variables together with the say extensive variables. And these thermodynamic variables can be easily picked up from a Gibbs-Duhem equation for the given system. When you see it here, when you see this equation here, you can see the variable pairs, which is called the conjugate variables: entropy, temperature, volume and pressure, and the number of moles and its chemical component. Okay. So because of this Gibbs-Duhem equation, you have only you have only C minus 1 composition variable, and then T and P as the remaining intensive variables. So as you see here, you may take the all intensive variables as the thermodynamic variables, or temperature, pressure, and then mole fractions as the composition variables. So in the lecture today, you will learn how to calculate each possible defect concentration as a function of, let's say, temperature, pressure, and then composition. By the way, let me make a small comment on this abbreviation. Probably, most of you have seen it for the first time. This is this means thermodynamics, actually first abbreviated by Clerk Maxwell. So whenever you see this short abbreviation, then please take it as the thermodynamics. Okay, now let's try to calculate defect structure of pure stoichiometric compound. Here, pure means really pure. Okay, no impurity at all, 100% pure. And then stoichiometric means composition is absolutely fixed. Okay, no, it is absolutely fixed, therefore no variation at all. Okay, let's take the sodium chloride as our example. Okay, then what are the thermodynamic variables of this system, sodium chloride? Because this system is assumed to be stoichiometric compound, therefore its composition variable is just none. Okay, because composition is absolutely fixed. Then you are left with the only two variables, namely temperature, pressure, okay, as your thermodynamic variables. So once you calculate the defect structure of your system, then each defect concentration will be represented as a function of temperature and pressure. Okay, now as far as the sodium chloride is concerned, the most likely defect, energetically, likely defects are Schottky pair, okay? Sodium vacancy and the chlorine vacancies. Actually, sodium chloride, I told you in the last lecture, consists of two interwoven face-centered cubic structure, one for the cations and the other one is anions. Okay? They are close packed. Therefore, in this case, Schottky pair has the lowest formation energy. Therefore, this Schottky pair makes the majority type of defect in this system. Okay, then defect structure means, as I told you earlier, each defect concentration, namely concentration of sodium vacancy and the concentration of chlorine vacancy, should be represented as a function of temperature and pressure. Okay, that's it. Okay, how do we calculate defect concentrations as a function of thermodynamic variables? here is the, so say, principle, to calculate the defect structure. Okay, number one, our system should be in thermodynamic equilibrium, which is often called internal equilibrium or thermal equilibrium. Okay, okay, then because of the entropic effect, there occurs the Schottky defect formation reaction. You see, ideal, suppose that you have the ideal lattice, then because of the entropic effect, as temperature goes up, of course, then sodium vacancy and the chlorine vacancy are formed. So for this case, you may apply the mass action law, namely the product of two concentrations should be constant, namely the Schottky defect formation reaction equilibrium constant. Let's call it K sub S. Okay? This is obviously, a function of temperature and pressure. Then once you write the unit of this defect concentration in terms of the side fraction, okay? As I said here, side fraction. Say vacancy, number of vacancies over the total number of lattice side, which is called side fraction. So as long as each defect concentration is given in terms of side fractions, then the equilibrium constant takes a quite simple form, okay, as you see here, namely in terms of the Schottky defect formation free energy. Okay? But of course, you see, you can often represent the defect concentration in terms of number per unit volume, right? So, or number of moles per unit volume. So in such a case, this equation should be modified by by adjusting the pre-exponential factor. So here I wrote how to transform the defect concentration in terms of side fraction into the number density. Here you see there is a constant conversion factor, beta, which is applied to the positive sublattice, and there is another factor, namely beta minus, which applies to the anionic sublattice. So this conversion factor is nothing but a constant, namely, have a look. Just divide, this is the side fraction, okay? And then to convert this side fraction into the number density, you simply multiply by the, so say, side density, okay? Then you simply transform the side fraction to the number density. Then in such a case, this pre-exponential factor should also be converted to the different, so say, number or pre-exponential factor involving these conversion factors. Okay, that's it. And then second, once the internal equilibrium is established, then always your system should remain electrically neutral, namely negative charge. The concentration of negative charge should be compensated by the equal concentration of positively charged defect. So here in this case, the sodium vacancy concentration should be balanced by the anion vacancy concentration. Okay, now you have two unknowns and you have two equations. The solution is just a piece of cake, right? So because this is simply equal to the other, therefore from this equation, you simply get the solution in such a simple form, okay? Now each defect concentration is given by a function of temperature, and don't forget this enthalpy. And actually, of course I will tell you later, this Gibbs free energy is a function of temperature and pressure. So each defect concentration finally expressed in terms of the defect concentrations via the Schottky defect formation enthalpy. Okay? So here's the solution. Now, if you say plot, say in terms of in the logarithmic scale, say ln of the each defect concentration is plotted against, say, reciprocal temperature to have such a straight line, then it's easy to recognize that this slope, okay, this slope makes the here, you see, delta HS over 2K, namely Schottky defect formation enthalpy divided by 2 times Boltzmann constant. That's it. Okay? So once you are given temperature, then you can calculate, okay, the each defect concentration. So you calculated the defect structure. Then you may ask, hey, what about the pressure effect? Actually, formally, you can calculate the temperature effect and the pressure effect in this formal way. You see, each defect concentration is given by given by this functional form, namely as a function of temperature and the pressure. Okay? Now, temperature dependence is simply obtained by taking the partial derivative of each defect concentration with respect to the, let's say, 1 over T at given pressure. Okay? You remember this kind of expression from thermodynamics course. This is the Gibbs-Helmholtz equation. So from which you can get the, enthalpy change, namely Schottky defect formation enthalpy. So at the given pressure, you know how each defect concentration varies with, say, reciprocal temperature with the slope of, the Schottky defect formation enthalpy divided by 2K. That's it. What about pressure effect? Yeah, again, you see, you can take the partial derivative with respect to pressure P at given T. Then have a look. You see, the pressure dependence of this Gibbs free energy is nothing but the volume change accompanying Schottky defect formation, which we call normally Schottky defect formation volume, or volume of Schottky defect formation. So depending on this Schottky defect volume, say you can actually you can calculate how much the each defect concentration varies with total pressure. So now you calculated the defect structure of pure stoichiometric compound. Quite simple. So far so good. Okay, what about the impure stoichiometric compound? Now you may find that it will be a bit more difficult. Actually, there is nothing absolutely pure because, for the thermodynamic reason, which I'll tell you shortly. Actually, if you mix the two components, let's say A and B, then there arises 3 kinds of solutions. Number 1, A makes complete solution together with B. So they mix so well across the entire composition range. And the second type is this also limited solubility. Okay? In this case, for example, component B is soluble up to only this much here. Okay? And then no more solution. So this is called the solubility limit. And likewise, A can be dissolved into the end component B by this much. Okay? Again, as you see here, this solubility limit is a function of temperature. As temperature increases, as you see here, the solubility increases. So anyhow, in this case, solubility is just limited. Therefore, we call it limited solubility case. Now, last case is actually negligible solubility. Now have a look. You see, no solubility limit is found. So you can say that, solubility is 0, but actually it cannot be 0 for the thermodynamic reason. So we say negligible solubility. Why is that? Here is the answer. Now suppose that your solubility limit is getting smaller and smaller for some reasons, okay? Well, it doesn't matter how small it is. What is important is it cannot make absolutely 0 because, because of the shape of the relative integral molar free energy of mixing, okay? If you plot relative molar free energy of mixing against the composition, then you can have, say, this kind of curve. Let's say, the solution involving the A as the host makes this kind of shape. Likewise, B solution has this kind of shape. Then by drawing a common tangential line, you can find the two, so say, coexisting faces here, likewise. As the solubility decreases, this mixing free energy curve is getting narrower and narrower, but still, don't forget, you see, eventually it looks like just this component axis. But if you expand this part, it still has this kind of minimum, okay? So if you take the slope at this this composition axis, then you end up with the slope of minus infinity. Actually, such a minus infinity slope. This means that anything pure is the sink of the anything else, because the other pure pure matrix or pure medium has the minus infinity chemical potential of the component I relative to its own pure state. So therefore, you see, any pure material makes a sink of everything else. So impurity is, I would say, of entropic origin. So in this world, nothing can be pure. Anything should be impure. Okay? That is simply for the thermodynamic reason, entropic origin. Of course, if you decrease the temperature down to 0 K, then if everything is in equilibrium, you forget about kinetics, then you end up with the absolutely pure, pure system. But as temperature increases, again, this T delta S term is growing more and more predominating. Therefore, impurity cannot be avoided. Right? Then how impurity, how is impurity incorporated into our host matrix? There are only two ways. Number one is to substitute the host atoms. So that kind of impurity is called substitutional impurity. As I wrote here, you see, in Craig-Vink notation, we represent them in this way. Let's say strange atoms or ions replacing M site, okay? Or foreign atoms replacing X site. And the second type is quite obvious. You see, impurity atoms or ions goes into the already empty interstitial site, so which is called interstitial impurity. And in terms of the Craig-Vink notation, you see, we represent them in this way. Strange atom, stranger on interstitial site, and here you see foreign ion on the interstitial site. Of course, you see there should be a charge state of this, impurities. But we will see what kind of value this effective charge or actual charge takes. Okay. Now, before getting into the real stuff, let's pause here to consider in which case we could make the so-called complete solution or wide enough solubility. Okay? To make the complete solutions, our end member component A and B should satisfy the following three conditions. Number one, okay? Both end members should have the identical crystal structure. But otherwise, what would happen? Consider that you have the FCC structure end member and a BCC end member B. Then you can easily imagine what would happen by replacing the host atom A with the impurity B, one by one, up to the B makes the complete system. Then you can see something illogical, right? So anyhow, to make the complete solution, the two end members should meet this condition. Namely, two end members should have the identical crystal structure. And the second condition, they should have the similar ionic size. One rule of thumb is that relative ionic size should be less than 10%. Okay? Otherwise, both end members tend to make the kind of interstitial impurities. Okay? You know why? If one has the size of this big and the other one has the size of such a tip, hey, can you imagine that this small thing can replace such a big one? It's really ridiculous, right? This small thing, as big as the tip of our ballpoint pen, tends to go into the interstitial side. By doing that, it can make the energy increase the minimum. Okay? So the second condition, this should be met for the complete solubility. And the third one, this is really important. Namely, regarding the ionic crystal case, both end members should have the same valence. Otherwise, you cannot make the complete solution. Let me take an example. Now here is the magnesium oxide, MgO. And here I would say Na2O. Okay, Na has the singly ionized, A1 plus, and the Mg doubly ionized, Mg2 plus. Okay, in such a case, they can never make the complete solution. Okay, so to make the complete solution, two end members should have the same valence. And for the case of metals, each end member should have the same electronegativity. Okay? Same electronegativity. If they have the quite different electronegativity, let's say one tends to be electropositive, okay? And the other one is a bit more negative. Then they tend to make an intermetallic compound rather than to make the solution. Okay, so these three conditions always should be met to make the complete solution. For the case of metal, you see, in addition to the number one and the number two, this condition should be met. Now we are dealing with the ionic solid. Okay, so normally you see the impurity. When we say impurity, normally our system normally does not make the complete solution. Okay, then let's consider how these impurities go into our host lattice. This is called the incorporation mechanisms. This is quite important. Okay, let us analyze how these impurities goes into our host lattice. First, we will deal with the lower valence impurities and then higher valence impurities. Okay, our host lattice is here MO, divalent oxide. Okay, for example, MgO. Now suppose that A2O is getting into dissolved into our host lattice MO. Okay. In this case, obviously, the cation A has the valence state of +1. Okay. Well, one real example maybe K2O into the MgO or something like that. You have to, activate your brain, in this step. How could we exhaustively enlist possible incorporation mechanisms? Okay? Here is one, I would say, kind of trick to exhaustively enlist the incorporation mechanisms. Okay, listen to me. Number one, okay. Now suppose that A cation substitutes M cation, and oxygen also substitute oxygen host ions. Okay. Now let's write down what's happening. You see, A replaces host M ion. M has the originally M has the +2 charge state. Now A is +1 charge state. Therefore, it has the effectively negatively charged, singly negatively charged. Okay. Now there are two. Therefore, due to the mass conservation, we create two substitutional A impurity. Okay, substituting host M site. Okay. Now oxygen replaces already existing oxygen site. Okay. And consider, don't forget, our host lattice MO, has the crystallographic structure of the site ratio 1:1, exactly 1:1. M site to number of M site to number of O site makes exactly 1:1. Otherwise, it could not be the MO. Okay. So to make our structure intact, there arises oxygen vacancy, one oxygen vacancy. By doing that, you see, you have two cation site and two anion site. Okay? So this is the first mechanism, possible mechanism. Then you see, suppose that you actually incorporated only delta impurity as much as delta. Okay, delta should be pretty much smaller. Delta A2O goes into the MO host lattice via this mechanism. Then you can easily write down the lattice molecular formula in this way. Okay? You can easily write down from this incorporation reaction mechanism. And the second possibility, A substitute the host cation, and the oxygen goes to I. Okay? So S and I, I call it SI mechanism. Okay, then A substitute M site to M site, and this oxygen goes into the interstitial site. What about structure? I used up two cation site, one interstitial site. Oh no, our structure should have the 1:1 site ratio. I need two anion site. That means I should have the two oxygen vacancies. What about the charge? Yes, oxygen vacancy makes the effectively positively charged by 2 units. Okay? Because oxygen has the actual charge of -2, and the vacancy has 0. Therefore, effective charge should be +2, right? Okay, now check the conditions, namely the site conservation. Okay, I use the 2 cation site and 2 anion site. What about the mass conservation? Yes, I have the 2A, here 2A, 1O and 1O. That's it. What about charge neutrality? Okay, I put the neutral oxide into the neutral host. Therefore, net charge on the left-hand side should be 0. Therefore, right-hand side should make the 0 net charge. Is it true? Okay. I have the 2 negative charge here and another 2, say oxygen interstitial, because oxygen has the actual charge of +2. Okay. -2. Sorry, -2. Therefore, it has the effective charge of -2. But oxygen vacancy, it has the 4+. Therefore, it satisfies the charge neutrality. Okay. Now, here is a very amusing point. You see, here are 2 oxygen vacancies and 1 oxygen interstitial. Oh, there are too many defects. This oxygen interstitial may go to the oxygen site to leave only 1 oxygen vacancy behind. So this is energetically more favorable, I think. Okay? Hey, it's interesting. This final result turns out to be equal to the first case. Of course, its lattice molecular formula turns out to be exactly the same as the first one. So actually, chemically, you cannot distinguish this mechanism from the second one. Okay? But anyhow, this is the second possibility. Third possibility, okay, the opposite possibility. Okay, A goes to interstitial site, and the oxygen goes to the substitution site. Substitution, okay? So A makes 2 interstitial, and 1O substitute, the already existing oxygen to make the neutral oxygen. What about the site ratio condition? Now I used up 1 anion site, but no cation site. Oh, then there should be created 1 cation vacancy with the effectively negative charge of 2 units. Okay? Here again, you see, we can consider. You see, to incorporate this one, you created 3 defects. Oh, energetically too expensive. If temperature goes up, this kind of things can happen. Let's say this interstitial A, 1A, goes to these vacancies to fill up this vacancy, leaving behind only 1 interstitial. Okay, so interstitial A makes the positively singly ionized interstitial cation, and replacing A impurity makes effectively singly negatively charged. Because monovalent cation replaces doubly valent, say divalent cation. Therefore, its effective charge should be -1. Okay. So in this case, again, you can check the site conservation, mass conservation, and charge conservation. And you can easily write down the lattice molecular formula as I wrote here. You can check. The last possibility, okay? So A goes to interstitial site, O goes to interstitial site, which is quite, say, trivial. It's so simple. So all A, namely 2A, goes to interstitial site, and oxygen goes to interstitial site also, and its effective charge is -2, and this interstitial cation has the effective charge of +1. Therefore, charge neutrality condition is satisfied, and structure condition, you don't have to worry about in this case because you used only interstitial site, no lattice site, so structure remains intact. Right? So in principle, there can be 4 mechanisms, namely SS, SI, ISII, for the case of binary system. Now you can imagine, how many different mechanisms are possible for the ternary, say, compound. Let's say AbO3. Okay, it's easy to imagine how many, such combinations can be made. Okay, but as far as the binary compound is concerned, these 4 possibilities are exhaustive. But chemically, these 2 mechanisms cannot be distinguished. Therefore, actually, 3 possibilities remain. Okay? Here, very important thing you have to remember. Whenever you write down this kind of incorporation mechanism, you have to satisfy, number one, site conservation constraint. Number two, mass conservation constraint. Number three, charge conservation constraint. Otherwise, this incorporation reaction makes no sense or turns out to be illogical. Okay? I introduced a Craig-Vink system of notation, right? A species sitting on the lattice side with the effective charge or actual charge C. There are three things, right? Now this condition means site conservation, you see, this side. Mass conservation, yes. Charge conservation, here. So three conditions should be met, don't forget. Okay? So this is what happens when you incorporate the lower valence impurities. Now let's consider the higher valence impurity case. Suppose that we incorporate, say, trivalent oxide, namely E2O3, into our host lattice MO. Again, we have two sublattices. Therefore, we can have only four possibilities which are exhaustive, namely substitution, and substitution, interstitial, and the interstitial substitution, and interstitial. Well, remember what we did with the low valence impurities. It's in the last slide. Again, you can write down the incorporation reaction as we did with the low valence case. It's quite easy. Now have a look. Okay, trivalent cation replaces divalent M. Make an effective charge of +1. Now we have 2E. Okay? Therefore, you created 2E impurities. And we have 3 oxygen here. That goes to 3 oxygen side. What about structure condition? Okay? We used 2 cation side and 3 anion side. Our host lattice consists of the 1-to-1 structure. Oh, then no way, except for creating the cation vacancies. Then you see you have 3 cation side and 3 anion side. 3 to 3 makes 1-to-1, right? So keeping our host lattice MO intact. What about the charge neutrality? Now you can easily check the charge neutrality. Now E has the unit, charge state of 3, +3, and M has the +2. Therefore, this impurity should have the effective positive charge of unit 1. Okay? And then you can easily write down the lattice molecular formula, as written here. Let me leave it for your pleasure as an exercise. Okay, second possibility. Cation substitutes, and anion goes to interstitial side. Okay, 2 cation replaces our host cation, and 3 oxygen goes to the interstitial side. Okay, to keep our structure safe, what should you do that? What should you do? Okay, you use 2 cation side. Oh no! What happened to the anion sublattice? Oh, then to keep our structure safe, you have to create 2 oxygen vacancies. Then you see, charge neutrality, satisfies itself automatically. Then, but as I told you, as we checked earlier, there are too many impurities. Too many defects. Here 2, here 3. Oh, how many? Oh, we have 7 defects. It's too many. Energetically too expensive. What shall we do? Our system is quite clever. They try whatsoever it is, to lower the energy of its system. So it's easy to imagine that 2 of this interstitial oxygen goes to this vacant side to make 2 regular oxygen, and leaving behind only one interstitial. Okay? So that this is the energetically more favorable because it's energetically cheap. Okay? This is the second case. Now you can write down the Lett's molecular formula in this way. Well, by using the mass conservation, you yourself try to derive it. And the third possibility, IS. Okay, cation goes to interstitial site, and the anion substitute the host ion. Now consider the structure condition. You used 3 anion site. Then what happened to the cation sublattice? To keep our host lattice intact, you have to create 3 anion site with no M. So 3 vacancies, so to say. Right? Again, you see here, you can see there are too many point defects. So the possibility to lower our system energy is the following. You see, 1E, this impurity. Oh, let's say that these two. Yes, these two goes to and occupies the empty host site to make the substitutional impurities, leaving behind only one cation vacancy. This is obviously, cheap, much cheaper energetically. Okay? Then it has such a lattice molecular formula. And last case is trivial again. You see, cation goes to the interstitial site, oxygen also interstitial site. So only 4 possibilities we have for the case of binary system. Okay? But here, you can easily you can see that the first possibility and the third possibility has the same lattice molecular formula. So these 2 possibilities cannot be distinguished chemically. Therefore, existing possibilities are only 3, okay? Namely, either one out of this one and that, and the rest 2. Okay? Now, again, let me emphasize here. Any incorporation reaction should satisfy the following 3 conditions. Namely, site conservation constraint, mass conservation, and charge conservation. Okay, don't forget. So this is actually, how the higher valency impurities go into our host lattice MO. Okay. Okay, this is actually an example which I would like you to try just for yourself. Okay. This is really famous incorporation reaction, namely the calcium stabilization of zirconia. Normally, to stabilize the structure of cubic structure of zirconia, you incorporate calcium oxide or yttria, into its host lattice. By doing that, you can keep the zirconia structure, in cubic. Okay, now again, as I told you, there are only 4 possibilities: SS, SI, IS, II. I would like you to try, how this result turned out. Okay. Okay. The last example, actually, this is the last topic of today's lecture. Let's then calculate the defect structure of impure stoichiometric compound. Our system is now, let's say, to be more specific, cadmium doped sodium chloride. To dope cadmium into sodium chloride, actually you add, say, cadmium chloride, to the sodium chloride. Suppose that you add the X mole of cadmium chloride to the remaining mole, let's say in terms of mole fraction, 1 minus X sodium chloride. Okay? This kind of, say, composition is called batch composition. Okay? Okay, in this case, what are the thermodynamic variables? Now, our system has 3 components. Look, NaCl and cadmium, right? We have 3 component. Then what about the thermodynamic variables? Of course, we should have the temperature and pressure as the, so say, already existing, variables. And then we add up the combustion variable. Because our host lattice is there just stoichiometric, okay? So our host lattice, combustion is already fixed. So there remains only one combustion variable, which is just the doping level or the amount of dopant, cadmium chloride. So if you calculate your defect structure, then you should have each defect concentration as a function of temperature, pressure, and X. Okay. We know that how cadmium chloride incorporates itself into the sodium chloride. In this case, they follows the SS mechanism. Cadmium substitutes sodium cation, and the chlorine, of course, sits on the chlorine side. This is the incorporation reaction. Now cadmium is divalent, therefore its effective charge is +1. Okay? And then 2 chlorine ion here. You see chlorine on chlorine side with just effectively 0 net charge. What about structure condition? I used up here 1 cation side and 2 anion side. Our host lattice, sodium chloride, has only 1-to-1 structure, right? So to keep our structure safe or unbroken, you have to introduce sodium vacancy. By doing that, you can make the sodium side, number of sodium side to number of anion side, 1-to-1. Then you can sort out what kind of point defect you have. Number 1, say sodium vacancy and the chlorine vacancy, and then cadmium impurity, which substitutes sodium. Now you need 3 equations because you have 3 unknowns here. Defect chemical logic goes like that. Number 1, now your system is in thermodynamic equilibrium. So therefore, defect formation reaction equilibrium should prevail. Okay? Now your host lattice is the sodium chloride is the close packed. Therefore, the Schottky defect formation equilibrium should prevail in this way. So the Schottky defect pair, the product of 2 defect concentrations should make constant. Schottky defect formation equilibrium constant. Equation number 1. Then your system should be electrically neutral, namely the sum of the positive charge should be equal to the negative charge. So condition number 2. And then finally, you should satisfy the mass conservation. Actually, the concentration or doping level of cadmium is already fixed. We know that because this is the initial batch combustion. So we know how much we incorporated cadmium into your host lattice. That's called the amount, just M, okay? Whatsoever unit it has. So you have the 3 equations for the 3 unknowns. Then it's easy to solve them out. Formally, you can solve this equation in this way. Okay, let's go back to this slide first again. You see, now this is the linear sum, and this is M. We already know that. Okay, because of this relationship, you can replace this, for example, chlorine vacancy concentration, with the sodium vacancy concentration by using this constraint. Oh, here is the relationship. Okay, what's that? This is nothing but a quadratic equation in terms of Schottky defect equilibrium constant, which we know, and then the impurity amount M. It's easy to solve this kind of quadratic equation, right? So finally, you end up with the solution in this way. Sodium vacancy concentration, should be given in terms of, say, impurity level and Schottky defect formation energy. Okay? Now, actually, this is a quadratic equation. Therefore, you should have the two solutions, okay, plus and minus. But as you see here, the minus part, cannot make sense because it gets you the negative value for the concentration. So it makes no physical sense. Therefore, it can be deleted. So you end up with only one physically acceptable solution. Let's have a close look at this solution. Okay, you see. Let's compare this doping level M with the Schottky defect formation equilibrium constant. Now this is squared. Therefore, let's compare M squared with Ks, or M with Ks to the power of a half. Okay? If Schottky defect equilibrium constant is much, much larger than dopant concentration, this is a practically pure system. Okay? Then you see impurity effect can be negligible. So sodium vacancy, concentration turns out to be equal to the half of Schottky defect equilibrium, like the pure, sodium chloride case. And then chlorine vacancy concentration, you see, due to the Schottky defect formation equilibrium, you end up with this solution. Okay, what a neat. Now, second possibility, the opposite to this case. In this case, impurity concentration is much, much higher than the, so to say, intrinsic defect concentrations, namely Schottky equilibrium constant to the power of half. Okay? Then in this case, impurity is predominating over the intrinsic defect concentration. Actually, this is why we call this regime as the intrinsic regime, even though our system is actually impure, but intrinsic defect concentration is predominating. So this regime is called intrinsic regime. And in this case, the opposite case, impurity is predominating. So this is called the extrinsic regime because impurity is of extrinsic origin. In this case, from this equation, you end up with this solution. Now, sodium vacancy concentration is fixed. In this case, the present case is equal to the impurity concentration. And then chlorine vacancy concentration follows in this way due to intrinsic equilibrium. So this is this, also formal solution. But if your system grows bigger and bigger in terms of the number of components, then this kind of the formal solution becomes quite complicated or actually impossible. Then how could we do that? Here is a simple method. Let me tell you just the essence. Charge neutrality condition is here. And impurity level is given, which we know. And then internal equilibrium condition. This and this looks fine. Oh, gee. This is just a linear combination of defect concentrations. This disturbs entire algebraic structure of this equation. Okay? It would be nice to have A equal B form. Then it's easy to solve, right? Here's the solution. Look, if you look at the charge neutrality condition, then you can easily see there can be two extreme charge neutrality conditions. Number one, in this case, say sodium vacancy concentration is equal to the impurity concentration M. And the second possibility, sodium vacancy concentration is equal to chlorine vacancy. What do you say? Then you see number one case, okay, let's call it number one, and let's call this one number two. Then two possibilities. First, solve by using this relationship. Then you can solve this simultaneous equation just by heart. Okay, result is here. So ozone vacancy concentration equal to chlorine vacancy concentration, and which is much larger than impurity level. And their concentration turns out to be equal to the Schottky defect equilibrium constant to the power of A half, okay? Because of this relationship. And second case, this one. Then so ozone vacancy concentration is fixed by impurity, okay? And then chlorine vacancy concentration, which is, a minor defect. So this, turns out to be like this. What's that? Compare with the earlier formal case. This case is much simpler, right? Much simpler. So this kind of limiting charge neutrality conditions is called Brouwer approximations, because Brouwer first proposed, this simple method. So in this case, this solution and this entire solution consists of two pieces of solution. So we call them piecewise solution. Okay. So to get the entire solution, you connect. Actually, you combine this solution and the second solution. Okay, in smooth way. So the result turns out, is given here. Now, let's draw the low concentration versus 1 over T again at given doping level M and the given pressure P. As temperature goes up, intrinsic defect concentration becomes more and more dominating over the impurity level. As temperature goes down, then intrinsic defect concentration gets smaller than impurity level. So you see, as temperature goes down, you tend to have the extrinsic regime, and at high enough temperature, you have intrinsic regime. Okay, in intrinsic regime, you have the solution, piecewise solution, this red line. Okay, simply is given as the half power of Schottky defect equilibrium constant. So its slope here in this case, as I showed earlier, this slope should have the 2k minus and Schottky defect formation enthalpy divided by 2k. Okay? And what about the extrinsic regime? Our piecewise solution gets you the cation vacancy concentration and then anion vacancy concentration. Then they meet here. Now general solution should be like this, as delineated by the, this curved line. So this is for cation vacancy, and this is for the anion vacancy. Now our impurity level is here. What about the slope of this part? Now this is 2 times of this one. Therefore, this slope should be delta HS divided by just the Boltzmann constant K. So that's why it is 2 times steeper than the intrinsic slope here. So this is the defect structure of impure stoichiometric compound. Okay. Actually, if you plot that theoretical solution, then actually you end up with this kind of black line. Okay. So by combining 2 piecewise solutions, you can get the entire defect structure. And what about the doping effect of doping level M? Here it is. Now suppose that our temperature is given. Okay, given temperature and pressure also given. Then when your intrinsic defect is much higher than the impurity concentration, okay? Then you are in the intrinsic level. So if you plot defect concentration against the impurity level here, this is M. Now suppose that a half power of Schottky equilibrium constant located here. So this means the intrinsic impurity, intrinsic defect concentrations. Now here you see, for smaller impurities, intrinsic defect is prevalent. Therefore, your defect concentration remains fixed up to this point. Oh, sorry. And then defect concentration increases, then cation vacancy increases in this way with a slope of 1, okay? Because cation vacancy concentration is equal to m. Slope is 1. Then what about the anion concentration? Oh, here it is. Now anion vacancy concentration varies in this way. You see, inversely proportional to the impurity level. Therefore, it makes this kind of shape. Okay? Now here somewhere 0. Okay, this is actually kind of piecewise solution. Then general solution may take, this kind of shape. For the cation vacancy concentration, you can, connect these broken pieces of lines in smooth way. And anion vacancy concentration varies maybe in this way. Okay? Yes, this is all. What a need. Okay? So actually, lower impurity level, your defect structure is actually, controlled by only intrinsic defect, namely in this case, Schottky defect. Highly, so say, impure regime, then you are in extrinsic regime. Then all defect structure is controlled by impurities. Now, let me finally point out this fact. When you say a crystal is pure, then that means, defect chemically, that means your system is in intrinsic regime. Okay? There is no pure crystal at all in this world because thermodynamics does not allow it. Okay? So whenever someone says, his specimen is pure, that means his specimen is in intrinsic level. Otherwise, all are, in extrinsic regime. Okay, so it's enough for today's lecture. Thank you so much for your attention, and bye-bye, and see you next lecture.